All right, we're recording. So I am so excited because today we are going to be going over 2.1, the derivative. All right, so we are officially in Unit 2. This is my favorite, most absolute favorite lesson to do in calculus. I'm so excited to finally be doing a video on it. So this is going to be fun. I'm glad to finally have it in some video form. It's a great little intro into what calculus is about. Right? So we learned limits. We learned about continuity last unit. That's great. That's awesome. But that leads mostly to our first big idea in calculus. There's really two main ones for us. Okay, derivatives and integrals. Derivatives takes up about half of what calculus is about. The derivative. So this lesson is super important. Now, I'm trying to keep it within 30 minutes if I can. So I might not be able to get to the examples, but at least I get to the core content of what a derivative is. So, all right, remember that idea that we've been talking about, okay? We talked about the average rate of change, and then we were trying to get to the idea of what an instantaneous rate of change is. And that's a derivative. So write it down. It is the instantaneous rate of change at an exact time. Okay. So normally with like average rate of change, we need like 2 points in order to do this, but we are looking at one exact time, and that's just going to be one x value. Okay, just one x value. This is the same thing as equal to the velocity or the slope of the tangent line. Okay, so beforehand we were looking at the slope of the secant line for like average rate of change. But when I'm talking about the slope or the velocity of the tangent line, that's instantaneous rate of change because it's at 1 point and not just 2 points. It's not an average anymore, it's an exact. Okay. So I'm going to draw a little picture here to kind of help us have a visual. So, all right, let me draw this graph pretty good here. I'm going to try that. All right, let's say we have that graph right there. Maybe it's some quadratic, whatever. Let's say we have the point, we'll call this point A. So then that y value would be f of A. And let's say we have like another point, we'll say like right here. We'll call that x. Okay. So that would be like f of x right here. Okay, now, what if I was curious about the slope at A? All right, if I was curious about the slope here at A. Well, before now, you would do it by finding the slope of the secant line. Which, let me draw that out real fast. Got a little line thing here. So the slope of the secant line between, say, A and X would estimate what that is. Okay. So what we're used to, I'll go ahead and write this out over here. We're used to doing the secant line. And just as a reminder, the secant line, all right, we would use the slope of the secant line to estimate the slope of the tangent line. Okay? Because we need 2 points to actually have a slope. There was no way to actually figure out the slope of the tangent line. So we used the secant line, and that was just our best guess. We did small intervals to guess pretty close. Okay? And remember how we did that. Okay? So m represents slope. So the slope of the secant line was equal to, and it was just the average rate of change, which was f of, and to write it in context of this problem, I'm going to say f of x minus f of a over x minus a, because those are the 2 points given in this graph. We'll just write it like that. Okay? So that's great. Now, it's just a guess though. So how do I work with this secant line? How do I get it to be the tangent line? Okay. Well, remember how we did examples before in class. That's the reason we did this. All right. So if I did like x to a, that's an estimation of the secant line. What if I had like decreased the distance by half? Or what if I had decreased that by half? Or what if I kept getting it closer and closer and closer to a? Wouldn't the secant line be getting closer and closer to the tangent line? So what happens if I were to keep picking closer and closer intervals? So much so that eventually I'm just going to be on top of a. Well, doesn't that sound like a familiar idea? Like if I keep decreasing the interval lengths, so maybe I do like x to a and then divide that by 2, divide that by 2. I'm getting closer and closer to a. X is approaching a. Does that sound kind of familiar there? What happens once x is on top of a? Then I have my tangent line. So let's think about how that works. So the derivative, or the instantaneous rate of change, okay, or the slope at an exact point, exact x value, is going to be equal to, it's still a rate of change, but to go from x all the way to a, I'm going to find the rate of change as x is going to be approaching a and eventually be on top of a. Well, how do we write that? We would say that it's going to be the limit as x is going to approach a of the average rate of change. And if I can find that limit successfully, I have found the point at which x is on a, and that'll be the tangent line at that point because we're doing it with the average rate of change. Isn't that cool? So this is equal to, and I'll write out the official formula now, the limit as x approaches a of f of x minus f of a over x minus a. That right there, all right, this is the definition of a derivative. That is the definition of a derivative. And then, like I said, that interval is going to be getting so small that they're going to be on top of each other at the same point that eventually we're going to have the exact tangent line. All right, so the idea is to take the limit of the secant line or the average rate of change until we are eventually on the tangent line, until we get that exact slope. Isn't that such a cool idea? We're combining average rate of change with limits to find the instantaneous rate of change. Love it. Now this formula is great. This is the definition of a derivative, but there happens to be two of them. Okay, this one's amazing. I think it's clear to see, but this is actually the one we don't use that often. We only use this when given f of x. And asked to find a specific x value. So this is helpful when like wanting to find it literally at one specific point. Okay? But the second formula we're about to talk about can do just the same thing and even more. So we typically tend to use that one more. So let's look at how that one is going to work. And it's the same idea. So this is the second formula. There's two formulas for the derivative. This is the second formula for a derivative. Okay. Now I'm going to use the same graph as before. I'm going to say, okay, here's my graph right here. I'm going to call this point right here A. All right, so this will be f of A. Now, I'm going to choose a point over here, but to help me write the second definition, I'm going to use different notation. I'm not going to call that x anymore. I'm actually going to call that, and a plus some distance between it. And we'll call that distance h. We'll call the distance between a and my second point h. So if this point is a, this point over here would be a plus h, the difference between it. Okay? So let's kind of go back to what we were doing before. Let's talk about like if I was doing just estimating that instantaneous rate of change at x. Let's say I was doing it by just finding the secant line between these 2 points. Okay, so something that we learned in the first unit. What would that look like? Okay, what would that look like? So the measure of, or the slope of the secant line is going to be equal to f of a, which I'm going to say is the second point. So I'm going to say, how about f of a plus h, and then minus f of a, so that's my y minus my y, and then over that first x value, so a plus h, and then minus the second value, a. Okay? So all we did is rewrite the measure of a secant line, just like we did in the previous example, but instead of using a and x, we're using a plus h and a. Okay? Same exact formula as before, just different notation. And the reason we do this is because notice what happens. The a's cancel on the bottom. So another way of saying this is f of a plus h minus f of a over h. Now, in the previous example, f of a minus f of x over a minus x, we know that's the average rate of change. Does this formula look very similar to some of y'all? You saw it in pre-cal maybe a little bit, sort of. This is called the difference quotient. This is called the difference quotient. Okay? So, again, we're using the same formula or the same idea as before. If I can keep making the distance between these points smaller and smaller, okay, if I keep making the interval smaller and smaller, so much so where they're on the same point, and we discuss a point approaching another point using limits, we can talk about the derivative again. We can say the measure of the tangent line, or the instantaneous rate of change, is equal to the limit again, but not of the average rate of change, but of the difference quotient. If I can spell it, I'll just say difference quotient. Okay? Now the limit as x is approaching what? There is no x in this problem. Okay? So if I want the points to be on top of each other, I want this point to get to this point, what does that mean is going to happen? It means that this x value here is going to this x value. So what's happening is you'll notice that h, which is the distance between the 2 points, will eventually have to go to 0. All right, once h is at 0, then a and a plus h are on top of each other, and we can find that limit and find the instantaneous rate of change. So we would say instead of x approaching a, we would say h approaching 0, the difference between the 2 points. Okay? So to write that out as this actual formula, this is the limit as h is approaching 0 of f of a plus h minus f of a all over h. That is another way of writing the same formula that I said earlier, but using different notation. And honestly, guys, this is the one that we use most often. Okay? There's a lot more you can do with this. The reason is because you can use this formula for everything. Everything including derivatives. So not at just a specific point. All right? You use this formula if asked for a derivative as a function. And that's going to be great because we'll be able to come up with a function that can tell me the instantaneous rate of change at any point on the original graph. So that's why I think it's the most helpful. Okay? So there's your 2 definitions of a derivative. And again, I think this one is the most important of the 2. And I think it's a really cool idea of where that comes from. It's just the average rate of change as we have a limit approaching a point. All right. Okay, so now that we know what an instantaneous rate of change is, and we know how to find it, we no longer need the average rate of change because we can find an exact answer. We got 2 formulas for that. All right, we've got 2 formulas, and we'll do examples of each of them probably together in class. I don't think I'm going to get to the examples. But it is used so often that it is called the derivative. Okay? So, the derivative of a function at a is notated as this right here. A way of saying this is saying f prime of a. If I say f prime of a, that is another way of me saying this formula right here, okay? Assuming that the limit does exist, and most times it will. Right? And whenever I say f prime of a, I am literally saying the slope of the tangent at x equals a. So it's no longer the average rate of change. F prime of a means what is the slope of the exact or instantaneous rate of change at x equals a. Now, since it is going to be the slope of a line, the equation of that line, right, we've estimated it in previous classes, but the notation I'm going to use is the point is going to be a and f of a, and the slope is going to be notated as f prime of a. That just means the slope at that specific point. So then our line is going to be y minus f of a equals f prime of a times x minus a, just the slope of a line in point slope form. I asked for the equation of the tangent line, and the AP exam asked for the equation of the tangent line so many times. They want to know the specific line tangent of the graph. So you just have to find the derivative in order to do that. We'll look at examples of this here later as well. Okay, so there is application with derivative, and we're going to do a lot more of that later, but I do want to go ahead and give you a heads up on velocity. Now, we've already talked about velocity with average rate of change. Okay, velocity is just a rate of change. It's the rate at which our position is changing. Okay, so let's write that. This is the rate that something, some object, some person, something, that something is traveling over an interval. Okay. So it's the rate that something is traveling over an interval. And we have certain notations for certain things that go with this. Okay. For instance, s of t. Now, don't ask me why they choose s instead of like p, because s of t represents the, we'll call that the original function. It's the position. So again, I don't know why they don't choose p of t, but they call it s of t. It's the position after some interval of time. Okay. Now, s prime of t is equal to v of t. S prime of t, or the derivative of the position, because remember, derivative is just rate of change, is going to give me v of t. So this is the rate, okay, or derivative of my position function. So again, derivative is another way of saying, you know, got that wrong. Derivative is another way of saying like instant rate of change. So this is the rate of change or derivative of the position function. Okay. Now there's some cool things with that. If the velocity function or the velocity value is greater than 0, what does that mean? It means we have a positive rate of change. So it's positive. In an application, that positive means things. It means that my person or object is moving forward, or it can mean that it's moving up or to the right. Those are all the positive directions. If v of t is less than 0, it's the exact opposite. It means that we're negative. Okay, meaning that my rate of change is negative, that we're going backwards. Okay, it could mean that we're going down or to the left. Those are all the negative directions. Okay. And what do you think it means, or if I say that the v of t, where t is time, is equal to 0. Okay, so that means that we're not moving forward, we're not moving backwards. My velocity or my rate of change is 0. So that just means we're at rest. Okay? So there you have it. Now, if I were to specify it as the instantaneous velocity, okay, the instantaneous velocity, that's just the rate at a specific time. So that would be like, maybe for example, like at x equal a or something like that. It's the rate of change at a specific point. So there's your application of derivatives. Okay? You do this by finding the derivative of s of t. All right, and remember that the derivative of s of t is the same thing as saying s prime of t, and that's just finding, which is the same thing as velocity. Okay. Now, again, we'll talk more about this later, but speed and velocity are pretty much the same thing. It's just that speed is a value that doesn't have direction associated with it. So like velocity can be positive or negative. That means you're going forward, backwards, or whatever. Speed is just like how much you're changing by without direction. So another way of saying that is like saying the absolute value of v of t, or the absolute value of s prime of t, which those are the same thing. Okay. And again, guys, we're going to go over all this and more application days later, but I just kind of want to throw this out here real fast, kind of like, so, because I might be using some of these words a lot, and I just want you to kind of know where I'm coming from with those. Okay? All right, let's keep going with this. So let's think about the derivative. Remember, the derivative is an instantaneous rate of change. It's a number, it's a value, it's telling me a slope. What is large? We have a large value for the rate of change. What does that tell you about the curve? How about that the curve is really steep? Okay, so the y values change rapidly. They change rapidly. All right, let me give you an example. I'll use this for all of them. Let's say we have this. Let's say we have that quadratic right there. Okay. Well, where is the rate of change the highest? All right, where is it the biggest? How about like right here? What about this instantaneous rate of change? If I were to draw a tangent line right there, wouldn't that be a very steep slope? That'd be like a large positive slope. Same thing over here. This is a very large number. It's just very large in the negative direction. So this would be like a large or steep negative slope. Okay. What about when the derivative is a small number? Okay, we'll think of it the opposite. Okay, the curve is relatively flat. Okay, or the y values change slowly. So in this graph, that'd be like maybe like right here, So here is that tangent line. Here is that tangent line. So I mean, this is a positive value and a negative value, but they're small or less steep slopes. Okay. And then what about when the derivative is equal to 0? What does that tell me about the tangent line? Is it steep? No, if the derivative is 0, that means that my slope is equal to 0. And what happens when your slope is 0? You have a horizontal, or I guess a flat, tangent line. So for instance, right here, that's flat. Okay? Now, at this point, there is no change in y values. Okay. And this is located, and you can probably already tell, this is located at extrema. So at maxes and mins. All right, at maxes and mins, a lot of times when you're changing direction from like a positive slope to a negative slope or vice versa, at a max or min. All right, it's that change in direction is when your derivative is equal to 0. All right, so just again, remember, can't stress it enough that a derivative is nothing more than the slope of the tangent line. Okay. Now let's look at one question with it, and then I'll save the remaining ones for class. And this again is nothing like crazy. Like we're not computing the derivative yet. In these problems, we'll actually compute derivative values. That's where the main math comes from. But this is a good problem that was pulled from an AP exam. Kind of. I mean, it was more multiple choice, but this is a good application question. It says for the function g, whose graph is given, arrange the following numbers in increasing order and explain the reasoning. So from smallest to largest. So let's think about this. All right, we got the value 0. We got g prime of -2, g prime of 0, g prime of 2, and g prime of 4. So remember, that notation means the slope at that point. Okay? So for instance, 0 is just 0. That's great. G prime of -2. So here is -2. The slope at that point seems to be relatively steep. So that's probably going to be a large number. Okay? So that's going to be a large positive number. Maybe the slope is 3, 4, 5, 6, maybe even 10. I don't know. It's going to be a big slope. But g prime is 0. Here's 0. The slope of the tangent line there appears to be negative. Doesn't seem to be the steepest in the world. Okay, but it's still going to be a negative slope. So that's probably like -1. I'm just guessing that's probably -1. What about g prime of 2? G prime of 2 is right here. Again, that's a positive slope. Okay, positive slope of that tangent line. But it's a little bit flatter than g prime of -2. So it's a little bit flatter of a slope. And then g prime of 4 is right here. Again, that tangent line looks to be positive, but it's probably the flattest one on here. So that's probably like a value like 1/2 or 1/4 or something, a very steep line. So let's put those in order, from smallest to largest. All right, starting with the smallest value, it looks like we only have one negative number, and that's going to be the slope at 0. So we'll say g prime of 0 is the lowest. And then we have 0, because there's nothing else that's negative. Then I would say that the next smallest number would be g prime of 4, because that's a relatively flat slope. So it's going to be a lower number. So I'm going to say g prime of 4. Then let's see, the next one would probably be g prime of 2, because again, it's a positive slope, but not quite as steep as this g prime of -2. So I'm going to say g prime of 2. And then lastly, I think the obvious one is this big steep one here at -2. So g prime of -2. Now, there you go. So there's a little intro into derivatives, and hopefully the idea of a derivative makes sense. We're going to actually compute and find the derivative or the slope at specific points in class tomorrow, or on Tuesday. So enjoy the lesson. I finished with 1 minute to spare, so I'm pretty happy about that. So y'all can go enjoy the rest of your day, and we will talk more about this later. All right? Forbes out.